In other words, CHOPS is in a dawn-dusk polar orbit. That means that it travels around Earth along the twilight terminator line with the sun powering up its solar panels on its back. Meanwhile, its gaze peers deep into space, protected from sunlight interference. CHOPS' mission allows the telescope to study the smallest exoplanets we know, called super-Earths. They can be as small as our planet, but can also be as big as Neptune. The goal of CHOPS is not to find new exoplanets, but to examine ones we already know about to determine what they are made of and how they are formed. And that is very exciting because it has the capabilities of discovering potentially habitable worlds, planets that might have a similar size, orbit, and composition to our home. CHOPS is much smaller than Hubble. It's only 1.5 m across and uses a 32 cm mirror. However, it can see exactly what the designers had hoped for. If you were to see those first images though, you might notice something peculiar. All the stars captured in them are blurry with no exoplanets visible. Now this isn't a design flaw. CHOPS is working as intended. The reason for the blurry images has something to do with the second method of exoplanet discovery, namely transit photometry. One of CHOPS's key instruments is a very advanced photometer that can detect the tiniest amount of light variations on distant stars. If an exoplanet's orbit is aligned with us, it will transit the parent star so that it covers some of the star's disk from our perspective in a similar fashion to a tiny eclipse. And that's what CHOPS does. It monitors the amount of light it receives from a specific star and then detects light variations from when a planet crosses in front of its disk to see how much dimmer it gets. The reason the CHOPS image is blurry is so that light from the star hits more of the camera sensor, increasing the number of pixels that get hit by the star's light. Through this, astronomers don't need to see the exoplanet itself, but this increased resolution allows astronomers to accurately record and study the star's light spectra itself, as well as any changes that take place from the exoplanet's transit. As you can guess, the bigger the planet, the more light it will obscure and the easier it will be to notice a dip in light intensity. For small planets, however, this process is much more difficult to measure, and that's why CHOPS is so important, as its advanced instruments and blurry images allow astronomers to better define the transits of those smaller, more Earth-like planets. Additionally, CHOPS can measure a planet's phase curve, or how much light it reflects from its sun. When a planet is in front of the star, it will block light. But as it orbits around the sides, it will reflect light back to us, which makes the star appear a little brighter from our perspective. Here, CHOPS photometer comes in handy again, this time to measure the increment in light variation. By comparing it to the light we receive when the planet is behind the star, when it's not interfering with the star's brightness, scientists should be able to isolate the spectrum of the light reflected by the planet. With that, they will be able to know the composition of the planet's atmosphere. And since they are investigating only the most promising planets, they can take multiple readings for a more defined measurement. But why does CHOPS have to be in space? Can't we do all these readings from Earth? Well, just like the James Webb Telescope, telescopes here on Earth face two main hurdles. The first one is that we have night and day. That's a large section of a 24-hour period where no observations can take place. We might miss an important transit during that time. But even at night, the light a telescope receives is distorted as it travels through Earth's atmosphere. Photons hit several particles in different layers of the air, making the light flicker and wobble. Even if there are several methods to counter that, the readings would never be as accurate as they would be in space. That's why CHOPS was launched into a sun-synchronous orbit. As I mentioned before, it will ride the terminator line of Earth. This not only allows it to receive constant light on its back for the solar panels to generate power, but it also means it can take a look at stars 24/7 without sunlight interfering with its readings. So, as you can see, with all the data CHOPS will hopefully collect, it may just be a matter of time until we can confirm the existence of another planet like Earth. A planet with similar mass and temperature, with the presence of water and oxygen in its atmosphere. All the right conditions that harbored life here. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast on the Characterizing Exoplanet Satellite. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McCone and this has been Astram. All the best, and see you next time. Heat, right now.